Good afternoon, everyone, and thank you for joining us today. My name is Kevin Satterfield, and I am the Marketing and Communications Specialist here in the Department of Civil, Environmental, and Geodetic Engineering. I'm filling in for Dr. Allison McKay, who would normally be greeting you today. She sends her best wishes. And we're pleased to have you at our kickoff for the 24-25 CEG CONNEXT quarterly lunchtime series. This program highlights creative and often amazing research that is happening right now here in the Department of Civil, Environmental, and Geodetic Engineering. And the full realized value and impact of the work that our faculty does occurs when research that they are undertaking informs practice and policy in the real world. So this CEGE Connect series is an opportunity to hear from some of these faculty members as they share their perspective on recent innovations that are relevant to that we hope will be relevant to practitioners. We're happy to connect with all of you today and to highlight the work that we're doing here. And we hope that will be a resource for you, whether you're an alum or a practitioner in industry, or maybe both. So to kick off our series, I'm very pleased to introduce Professor Gil Bohrer. Dr. Bohrer's research integrates hydrology, ecology, and atmospheric dynamics. He combines experimental data collection with the development of numerical models to better understand plant species level atmospheric exchange of water by vegetation, also atmospheric exchange of greenhouse gases and water between forests and wetlands, as well as particle and animal movement, rather, in atmospheric systems. I usually, when I'm speaking with potential collaborators or students about Professor Bohrer's work, I usually cap that off with just saying his team does really cool stuff. So today he will be sharing perspectives in a talk entitled Understanding Ohio Wetlands Greenhouse Dynamics. As always, you're welcome to drop questions into the chat function if you'd like, or you can reserve those for the end of the talk where Professor Bohrer said he'd be more than happy to take a few minutes to answer questions. So I'll turn it over now to Dr. Bohrer.
So I assume you can hear me well and can see my screen. Let me go into presentation mode. There we go. Still seeing the right screen? Okay, so of all the different things that I do today, I'll focus really on Ohio wetlands, but specifically on one very special wetland, which you see here in the picture. And I can't check. Oh, I use. Okay, figure out how to change slides. So the research that I'll show you today was all based in Old Woman Creek. This is the Ohio National Estuarine Research Reserve. The NER system is a national system. There's a NER at almost every state with a coast. Some don't have it, some are just getting new ones right now. So the Ohio NER Center, NERs are run by NOAA but operated locally. So the Ohio Department of Natural Resources is operating Old Woman Creek, which is the Ohio NER, and it's also a state nature preserve, so no development, no fishing, no hunting. This is really just to appreciate nature and to study. And I added some different pictures of people of my team doing research at different seasons of the year. So what kind of methods do I apply in Old Woman Creek and generally at wetland research? So I'm combining atmospheric fluxes, which are measured from that tower that you see here that we built at Old Woman Creek. Challenge there with, this is an eddy covariance tower. The trick in eddy covariance is to measure the vertical flow of anything from the surface to the atmosphere. Can be negative verticals, could be things coming from the atmosphere into the surface, think CO2, for example, or methane, water vapor leaving the surface into the atmosphere. So we have this big sensor is a gas analyzer. We have smaller sensor, as you can see here, which is an ultrasonic anemometer. So with 10 Hertz measurement of the gas concentration changes and the wind direction changes, we can correlate the vertical wind flow with the change of concentration, which can be backed up mathematically using the covariance of vertical wind and gas concentration to an accurate calculation of exactly how much was flowing upward as measured by this gas analyzer. So this big gas analyzer measures methane. There's a smaller one here that measures CO2 and water vapor. And then there's other meteorologicals. This is a temperature and humidity probe. This is a radiometer that we're trying to measure the environment around the wetland while we were doing our gas flux exchange measurement. That will give us picture from a large mixture area upwind. So as the wind blows towards the tower, something is leaving the surface, mixing upward, upward, upward until it's crossing my sensor path. So I get a kind of a large scale picture of gas exchange from the wetland upwind of my tower. However, to make accurate measurements that are specific to points in the wetland, so if I want to know what comes from a particular plant type or how depth influence the flux at specific points in the wetland, we're using chamber measurements. Here we have a gas analyzer, not different than that one. This one is an open path. The wind is pushing the gas. This one is powered by a pump. The pump is sampling the airspace that's recirculating here in this chamber. Once we close the chamber, whatever comes from the surface accumulates in the chamber. From the accumulation rate, we can calculate the rate at which methane, CO2, or water vapor was emitted into the chamber. So we can have both very small-scale measurements and relatively large-scale measurements of gas exchange. Now, Old Woman Creek is typical, but also special and unique in a sense. So around the Great Lakes, because the Great Lakes is a very sandy environment due to its glacial past, we have a typical situation where an estuary of a river gets blocked by a sand dune that's deposited by the lake. So if the wave direction and the wind direction in the lake is just right, the lake will deposit that kind of a coastal sand dune. And if the river is not very big, it can block the river, and that creates a wetland. And that's exactly what Old Woman Creek is about. It is not the only one. There are other wetlands like that around the Great Lakes. They are very rare because coastal property have developed. Most of these wetlands are now extinct. So it used to be a relatively common form of an estuary of a small river in the Great Lakes area. Now it's quite rare, but there's still a few of them in existence. Old Woman Creek is a relatively well-preserved one, but it is the estuary of a very agricultural watershed. So when the barrier is open, the wetland is very shallow and it's about the same height as Lake Erie. When the barrier is closed, the wetland water elevation is rising. And as the barrier is deposited higher and higher, the wetland can grow higher and higher. Every now and then there's a big rain event. The water, the wetland rise very, very quickly and then topples the sand barrier, erodes the sand barrier away and opens it. And we're going through cycles of very, very big changes to water elevation. So typically wetlands are regular wetlands that are permanently flooded. They fluctuate 10, 20. So water elevation fluctuation is expected to be around a foot. So wetlands are defined different than lakes by being shallow. So we expect wetland water depth to be between 0 and 2-3 feet with not too much water level fluctuation. Old Woman Creek, as you can see, fluctuates by about 6 feet, up and down within a matter of hours. So here is an event of barrier break. So the rain event brought a lot of rain. Very quickly, the wetland went up and then toppled the sand barrier and drained to the lake. And it does it again every few weeks. Of course, there's some gaps in the data, but data in nature is hard to find. So another thing that Old Woman Creek is special in is very, very strong methane flux. And kind of, as I started my career, I was working in a small wetland here on OSU campus. I figured out that wetland is too small. I need some big place. And I'm like, okay, let's go to Old Woman Creek because it was nice working with them. It's run by the ODNR and they're very, very nice to work with. So I went there assuming it's kind of a typical characteristic wetland will give me a fantastic way to work and improve the model that I'm working on, but completely not. So this is each point here is a different wetland. This is a collection of All the natural wetlands where long-term fluxes of methane were collected using the eddy covariance technique and not the chamber techniques. They typically don't give the same results, and scientists are still arguing as to why. But if you measure with eddy covariance, these are all the sites that were collaborating in 2021. Now there's about 2-3 times more sites than that. But as of 2021, when they created the FluxNet CH4, which is the first data sharing network of eddy covariance sites with methane, Old Woman Creek was here. So this plot is plotting the typical relationship between mean annual temperature and mean annual methane flux. As you can see, Old Woman Creek has the highest observed methane flux. And please notice this is a logarithmic scale. So being about a log above where it should be and about half a log above anyone else. So it's extremely high methane flux. And I still don't know that I understand fully why is it so high, but we'll get to my latest hints and suspicions by the end of the lecture. Excellent. So this was a demo that my former student Camilo Rey Sanchez and Tim Morin recorded with a program called AquaKid. It's a YouTube kind of channel, science education. There are now professors. Tim is in SUNY ESF and Camilo is in NC State. And the fun thing is that it completely exploded, burned their faces. Lucky that I wasn't there, so I can't be held responsible. And nobody expected so much methane. It never does that. It's kind of a cool little demo. You see a little flame, not such a huge explosion. And that's the cool stuff in Old Woman Creek. So what do we care about methane so much? Here is the most iconic IPCC chart. I know that maybe you are not climate geeks as much as me, where IPCC charts get to your iconic concept levels, but the IPCC is the Intergovernmental Panel for Climate Change. They are a body of the UN where scientists from every country are sitting together and arguing out what do we know to this point about climate change impact, about climate change modeling, what is our best state of knowledge that we can project climate for the next 100 years. Every 5 years, they publish a report. The latest report that was published is AR, they call assessment report. This is from the 6th assessment report published in 2021. The next one, AR7, is about to come out. And they always show this plot putting all the different things that humans do to affect the world climate, all of them put to the same unit of degrees. So currently we know there's a total impact of greenhouse gases of about 1.5 degrees, of which 1 degree is expressed, and then 0.5 degrees offset by other things that we do, like deforestation and polluting the atmosphere with sulfur, which is highly reflective. So of the greenhouse gases, CO2 has the largest impact, and it's creating it's elevated our temperature today. These are not future projections. These are of the current temperature increase, what is attributed to CO2, and that's about 0.75 degrees Celsius or about 1.5 Fahrenheit. And methane is following close second with 0.5 degree Celsius or about 1 Fahrenheit. So this is the effect of methane. And methane comes from 3 big sources: agriculture, oil and gas industry, and natural wetlands. And of the natural sources, natural wetlands in general are responsible for about 60% of the natural sources of methane, which is about half of the total methane fluxes. The other half are from industry and agriculture. So now let's go to a little wetland, understand what's going on with greenhouse gas dynamics in the wetland. So again, it is actually not very simple. There's multiple processes, they're all interacting. So the easy thing that everyone knows is photosynthesis. Plants are growing and they're green as they collect sunlight, and they use the sunlight to synthesize sugar. So they capture CO2 from the atmosphere. That's gross primary production. Here, that's the CO2 that comes out of the atmosphere. and they deposit it either in their stems or exudate it in root exudate. So they kind of leak sugar through the roots to attract bacteria that work near the roots and benefit the plants. So some of it get trapped in the soil as plant material as the plants senesce, drop their leaf, they die, the stems don't fully decompose. So some of it is sequestered in the soil. Some of it, especially the sugar exudates that are in the soil, are being eaten by bacteria. Now, if there is oxygen in the soil, the bacteria will eat the sugar and breathe it out and emit CO2 back out. If the soil is anaerobic, as happens in wetland, because the water block the infiltration of oxygen from the atmosphere to the soil, so the soil becomes anaerobic, no oxygen in the soil. So other bacteria, and actually archaea, not bacteria, that are eating, can eat away those sugar, ferment, other bacteria ferment them, the sugars ferment them to alcohols, and then the fermented alcohols can be eaten up by archaea that create methane. So methane is accumulating in the soil. As it's accumulating in the soil, it can move slowly to other parts of the soil where there is some oxygen, and especially near the roots, because the plants transport oxygen down the stem, otherwise the plant roots will choke. The plants need to breathe too. And that methane is then itself being eaten by the bacteria and turned to CO2, or it can slowly diffuse through the water and get to the air, or it can bubble out because there's so much of it, and you've seen the bubbles in the YouTube demo, and get out to the air. Methane can also escape out through the plants using the same pipes that the plants have to let oxygen in the roots, allow methane to escape out. And as the methane is moving through the water, either by diffusion or in bubbles, the water itself, especially the upper part of the water, is aerobic, and the methane again can be eaten away by bacteria and turned to CO2. So we have a very active dynamic between CO2 uptake by plants, CO2 emissions by plant and bacteria, methane emission by bacteria, and then methane turning into CO2 again by bacteria. And we need to understand all of that to actually be able to predict. So if we were to write a model that can predict how much methane is coming out of a wetland, that model will need to represent what the plants are doing in terms of moving methane and moving oxygen and uptaking CO2, what aerobic bacteria are doing in the soil in terms of breathing the CO2, breathing the sugars back into CO2, and what anaerobic archaea are doing in terms of turning CO2 into methane, and then there's other form of aerobic bacteria that's turning methane back to CO2. So all of them need to be represented. This is all a function of the water depth, the soil density, the vegetation, how strong is the wind mixing the water, so how much oxygen moves through the water. It becomes very, very complicated very, very quickly. And this is why models of methane in wetlands tend to be highly inaccurate. One big problem of wetland methane models is that models want a simple picture. And so they want a wetland. Typically, all biogeochemical models that work on bacterial decomposition of anything in the soil will be a 1D model, where you have the atmosphere, the water, the soil. So all we care about is the depth of the soil, the depth of the water, vertical diffusion only, and this is all like 1 pixel wetland. But in reality, this is not one wetland. Even Old Woman Creek, which is relatively small, has different characteristic patch types. Each of them behaves very differently. So here's a picture from 2018. So you see there are small patches of cattails, there's large patches of lotus, there's large patches of American lily, and then some swath of deeper open water. And each of them has its own behavior. So to start addressing that, we created a model that can process remote sensing images. So we have weekly remote sensing images from the HLS product, which is combining a European Sentinel satellite with the NOAA Landsat satellite. And we can process the seasonal time series of HLS to see the seasonal rate of greening. So different plants have different timing of the greening. So some plants start very early in the season, some plants late until later in the season, some plants senesce much more slowly and are kind of more brown when they senesce, whereas water lily just sink in the water. So throughout the season, they behave differently. We can pick on those differences and create repeated annual maps of which patch type was where at what year. And as you can see, as the water level in the wetland increase, those patch types are radically changes, where in 2016 we were mostly cattails. In 2020, there's no cattails whatsoever, and we're mostly lotus, which kind of prefers the deeper water. So water elevation by itself has an impact. As you can see, this is a super noisy regression. So this is not to say that water elevation is the only thing that explains methane flux. In fact, explain only 12% of the noise of methane flux. But clearly, in the days where the wetland was very, very deep, the methane flux was very, very small. And the days where the methane flux was very, very high, these was the times where the wetland was shallow. So common knowledge is the exact opposite, that with more water, you will get more methane. But common knowledge is coming from very shallow wetlands where less water typically means that the water table depth is below the surface and the top of the soil is exposed to the air. Old Woman Creek, especially since 2016, where Lake Erie level went up, Old Woman Creek is permanently flooded. So given that it's flooded with at least half a foot of water above the soil surface, as we get more deepening on top of that, we're getting less and less methane flux. We think because it takes the methane more time to move through the water and it's being eaten by bacteria on the way, or because it changed the vegetation type and the cattail allowed methane to escape out more efficiently than water lily. So kind of working on that theory, we know that different water depths create different vegetation population. So very shallow water where the water table depth is sometimes positive, sometimes negative, will create a mud flat. A little bit deeper, you get cattail. A little bit deeper than that, you get floating vegetation like water lily and lotus. Very deep, there'll be only submerged kind of algae and submerged vegetation with an open channel. Old Woman Creek has all of these, but since 2019, we lost that shallow part. It all became deep because the bank is very steep. So here's a map of a sampling location we did in 2018. We looked at different locations at the wetland. Some of them are shallower, some of them are deeper. And again, remember, shallow, intermediate, and deep are associated with different vegetation types, but depends what the actual depth, which type, or depends what year you come. A different year, there were different vegetation types at each location. So the relatively shallow locations here, for example, in 2016 were all cattail, in 2020 were mostly water lily. The much deeper locations were always open water, but then started having a lot of lotus by 2020. So while the vegetation type at each of those places changed, the relative depth is the same. And we use a core. We stuck a big core in the mud, sampled the mud, use lead to date the mud, so to know what year each layer of the mud got deposited, and measure the carbon concentration in the mud to know the sequestration rates in the wetland. And here's the answer. Very, very different sequestration rates comparing the shallow and the intermediate. And the intermediate experienced the largest move of vegetation types. And then the deep, which is relatively stable, sequesters the most. So what do those plants do? This is the plant parenchyma. This is the tissue that plants have that's used to move the oxygen to the roots so the plant will not choke. Methane can abuse those pipes and escape out of the soil. And when methane escape out from the soil through the plant, is much faster than slowly diffusing or bubbling through the water. So the chances of the methane being decomposed back into CO2, if it goes through parenchyma, is much smaller. And this is, again, my former student, now professor in Lafayette, Louisiana. He developed these very high-tech, Walmart-based tapestry-type chambers to measure flux to know exactly how much flux come per leaf area of different vegetation types. So as we were working on that, we saw that the cattail has the highest conductance. So methane has it easier to move through cattail, especially late in the season, whereas lotus and lily have much lower conductance, and it's harder for methane to move through these plants. Other things that was, again, challenging modeling for lotus and lily, that conductance per leaf area was kind of flat, whereas cattail increase leaf area, but also increase conductance at a higher rate than leaf area increase. So as it ages, kind of the branches become less dense and more things can move through them. We can observe leaf area from satellites. We can force our models of wetland with observed leaf area, but creating a behavior like that is a little bit challenging. Behavior like this is much easier. Here is Madison Evans, an undergrad in this department. You can see we treat undergrad well and take them to super fun activities. So she's plucking out one of those. We design a special soil water peeper. It kind of allows us access to different points within the soil where we can let the water in cells inside that equilibrate with the gas concentration of the water outside. There's a membrane that prevents direct exchange of water. So we're just looking at the solute concentration of the pore water. We can then sample it. So now we can combine measurement of flux to the atmosphere with understanding of long-term sedimentation rate with understanding of instantaneous. We need about 2 weeks for it to equilibrate, but more or less weekly or bi-weekly scale of the concentration of carbon and methane in the soil. And what we found is that they are very much correlated with dissolved oxygen, but with a big surprise. So the red triangles are methane. So when there is less oxygen, we found a lot of methane, but suddenly near the surface, there was this spike, unexplainable spike in methane where it shouldn't be at all. So you would expect more methane to be in the deep soil. Where, do you even see my mouse? I think I should be pointing here. There should be more methane at the deeper parts of the soil where there's no oxygen, and there should be zero methane at the aerobic parts of the soil where oxygen allows bacteria to decompose the methane and breathe it out. But we found the opposite. This we publish in Nature. We call it the methane paradox. We show high methane production in the aerobic zone. We explained it through heterogeneity of soil density. So even in this area, which is on average aerobic and have oxygen, there are small clumps of the soil with bacteria living inside the clumps in the crack between the soil particles. And those tiny little clumps stop the oxygen from diffusing with the water and become locally anaerobic. The advantage of being here is that the other bacteria that process the complex sugar into alcohols are all working here. So there's much more sugars in that area because you are near the surface and near where most of the roots deposit, and we see a lot of deposition of sugars from the river water. So here's where you have most food, and if you can find local refugia from high aerobic locations, you can be a very successful anaerobic methanogen that makes methane, even though you're living in a largely aerobic area. So now we have all of that knowledge and we come to applications. So what do we do with all of that? So we know that wetlands are not one thing. So in my world, to be successful, so in the world of climate, our climate predictions, so if we want to incorporate the knowledge of wetland methane emission in climate prediction, the tools that are making climate predictions are Earth system models. Earth system models combine atmospheric dynamic, ocean dynamics, hydrology, snow and ice, human behavior and emission, land cover, land use change, both natural and anthropogenic, and all together trying to imagine a picture, a very realistic picture of the world tomorrow, a year from now, 50 years from now, 100 years from now. So all these climate projections that you see from the IPCC are made by ensembles of many different such land surface models. We don't believe any of them particularly, but all of them together can, on average, can't be all wrong. So we assume that the errors cancel out to some degree and that an ensemble of model will perform better than one. I particularly work with this Earth system model. It's one of the newer Earth system model, won the Gordon Computational Prize 2 years ago, and it is included in the assessment report 7 of the IPCC as one of the tools for future climate prediction. It's called E3SM. It is run by the US Department of Energy, and developed in multiple national labs, PNNL, Oak Ridge, Los Alamos, Berkeley. They all work together to develop it. It has many different components. One of the key components is the land components where wetlands live. So I'm working in the land component. The land component is called ELM, which is the E3SM land model. Very imaginative name. So here is a very, very simplistic representation of how ELM sees the surface. So in every ELM pixel, which will typically be maybe 1,000 by 1,000 kilometers, so we divide the whole world into these pixels. They are not very small, maybe 100 by 100 kilometers at a high resolution run. So that resolution, the surface is a mosaic of different land units. Now there is a vegetation land unit, which will activate the ecosystem model. There's a lake land unit, which will activate the land model. The lake model, there's a frozen land unit. It has its own model. There's an urban model. There's an agricultural model. There was no wetland land unit. So the way wetland was handled is if a vegetated soil got flooded because of local rain, and this model is not connected to the river hydrology. So there were no riverine floods of wetland, just the local rain is enough to saturate the soil. Then the biogeochemistry of wetland kicked in the wet soil component of the dry land vegetation, which is very, very not wetland at all. So we created a wetland land unit. The nice thing about wetland land unit, it has its own plant functional types, which are characteristics of wetland. So it has cattail, it has floating vegetation. When I'm saying it has cattail, it has plant functions that have parameters that create behavior similar to what we expect of those plant types. Unlike the vegetation, the ecosystem model, the functional type within wetland are not characterized only by their vegetation type, but also by their hydrology. So they have different typical inundation depth. And we changed the model to allow to enforce realistic flooding. So most wetlands are very, very small. They're not 100 by 100 kilometers. And the reason they're flooded is because of microtopography. They're in there's small areas of depression in the land which get filled with water. Again, imagine a pond. So we create a parameter of inundation depth, and we stop the model from creating runoff so the water can get to the surface. At that point, the model would typically let it run off. We prevent it until the water reach that maximal inundation depth, which is typical for different plant type. We improved the characteristics of the plant. We added the conductivity of movement, the conductivity of the plant tissue to movement of methane from the soil as a function of leaf area was added as a property of the plant types. It wasn't there before. And then by doing all of these things together, we managed to create a very, very realistic model of methane emissions. So go through this complex curve slowly. The purple line, it's not at the beginning. We only have almost like about a year and a half of observation. This is that purple line here, and then the shading around it, that's the uncertainty of that eddy covariance observation. It's not very accurate way. Here there was a hurricane, that blue line, we changed kind of everything. Before the hurricane was a period of drought. Now, I didn't say it, I'm saying it now. This is not Old Woman Creek. This is a simulation of a wetland in Louisiana. Why did we not simulate Old Woman Creek? Honestly, because we failed. Old Woman Creek produced so much methane, no matter what we did, what crazy parameter values we put, we could not convince a model to emit so much methane as Old Woman Creek is predicting. And because a very good student was working on that and there was no point of making her fail her thesis because of nature is weird, she used another wetland to show that the model can be accurate if given a reasonable site. So this is a Louisiana, Mississippi Delta kind of floatant marsh, very typical wetland to that area. And again, purple line with is observation with uncertainty. The orange line here, that's the original model out of the box that doesn't have explicit wetland. You can see it's completely all over the place. So it's very much off. As we put our new version of ELM, which include that wetland characteristic, inundation depth, and different plant functional type, that's the yellow line, we got closer. Where did we run into problems? In this depth of the drought period where the wetland was almost dry, our model didn't think the wetland should be as dry because in the model, the water balance is local by precipitation and saturation of the soil. And the reason here is that the upriver water management closed the gates and basically dried the wetland because we were in a drought period and they were not releasing water from the reservoirs. Then came the hurricane and flooded the whole area, and that the model managed. So that was by local precipitation, and the model managed to capture the behavior after the hurricane, but not in the drought before. So then we added another sophistication to the model. In fact, it's making it dumber, not smarter. We tell the model, okay, we don't trust you in predicting the hydrology. Again, this is a collection of 1D models. There's no true hydrology there, and definitely not water reservoir management. So we don't expect the model to know the correct water elevation, but we will tell you the correct water elevation. And by prescribing the water elevation, we managed to get the drought right and the hurricane right, and are overall very, very accurate. So if you look at the green, it is very, very close to the purple. And these are just the statistics. Original, we want the slope to be 1. Slope of 1 means that observation is equal to the model. We start with a slope of less than half, giving wetland vegetation type and get us to a little bit more than half, and prescribing the water elevation got us to 3/4, which again is very good, specifically in the world of methane, which is extremely hard to predict. So now, why are we failing Old Woman Creek so miserably? I need to show you this is an annual carbon budget of Old Woman Creek, or at least the components of it that we know. So this is the net ecosystem exchange. This is the difference between carbon coming in by photosynthesis and carbon going out by respiration. This is the amount of carbon that left the atmosphere and went into the vegetation and the soil. Whatever that means, it's around 32 teragram of carbon per year. Okay, it's a number. Don't need to remember it. But I want you to notice that the flux of the amount of carbon that goes out as methane is almost 20% of that. So it's almost 6 out of 32. And that's insane. In the typical parameter, the typical carbon use efficiency of the methane processes is 1%. So it should be 1/100th of that, not 20% of that. Typically, methane is measured in nanomole and carbon is measured in micromole. These are large numbers because we multiply it over the whole wetland the whole year. But no model ever can produce such a high number. It's almost stoichiometrically unreasonable to have such a high number. So what else is going on? So we started to suspect the fact that we are in an agricultural watershed, and we know from other measurements in other sites, that sites in agricultural watersheds can have very, very high methane flow. So we're starting to suspect that DOC, dissolved organic carbon. So these are sugars coming down the river. The rainwater is collecting them from the field. They flood the field, run off to the ditches, then join the river, make their way down the river to the wetland. If you notice, they're about 30% of net carbon exchange. So they increase net carbon exchange by a quarter. And it's a huge, again, it's a huge number. I want to say this number and that number are fantastically large relative to what you would expect in normal clean wetland. So we are suspecting that it's possible that the type of sugars that come down with the dissolved organic carbon are particularly likable for the methane process, or that if we put these two together, methane is becoming more likely. Another thing that we see, the long-term carbon sequestration relative to that incredibly high rate of carbon leaving the atmosphere, entering the system, there's a relatively small amount that stays in the soil. And that's, again, unlikely. So this is about 10%. So it's 90% less than what we expect. We expect all of this to stay in the soil. Otherwise, whereas it's going, okay, some of it is making methane, but this minus methane should be the carbon that stays in the soil. And it's not. There is so much less. So now the question is, what's getting out of the wetland? And that's a very, very hard thing to calculate. So it's possible that there is more carbon leaving the wetland as DOC than entering, because if you add DOC to NE, subtract methane, subtract sequestration, all of that should be leaving the wetland somehow. And we suspect is leaving it either when the barrier break and the wetland suddenly empty and the whole wetland drain. It can be scouring the soil and kind of picking up carbon that's already deposited in the soil, throwing it in the lake, or that a large amount of dissolved organic carbon is seeping through the sand barrier when the barrier is closed, so there's a constant leakage of carbon out of the wetland. And this is the component that I'm working on now. So my incoming student, my batch of incoming student is all about that DOC outflow. So we just measure the hydrology of the sand barrier. We're trying to work on a model that predicts the exact elevation head difference between the wetland and the lake, trying to understand the nutrient condensation in the exfiltrant to know how much is leaving the wetland so we can close this budget. And then we should enable a model to incorporate DOC inflow and outflow. And by that point, we may have some chance of predicting methane flux from a wetland like Old Woman Creek. Now we landed here. This is a group of high school students that we had for many years a summertime project of high school students coming to help us maintain the towers. We need to go there every 2 weeks, clean the sensors, collect data, tighten the guy wires. They really loved it. It's a very nice site to work at. And I'm open for questions.
Thank you for great presentation, Professor. Yes, questions, anyone?
I stumped them.
Gil, if I may ask a question, you talked about your student using data from, I believe it was Louisiana. How did that site in Louisiana was selected? Can you tell us a little bit more about
yes. So the site in Louisiana is the USGS Water Center. And basically, we need a site where we measure the fluxes of carbon and methane exchange with the air. There are very few sites that do that. So almost There's a few sites in California, but we were collaborating. So the site selection wasn't driven by science of which wetland do we most need to know, but by convenience, which wetland site are we collaborating with that have the data that we need to validate our model. So Jorge Villa, which again was my student, made a kind of peeper and chamber measurement that we need to calibrate the patch level data in the model. And another collaborator, Eric Ward, that was at the USGS at the time, now in NASA, was running the eddy covariance observations in that site. And there were 3 sites in Louisiana that we were working with. One of them had 2 tall trees, so they didn't build the eddy covariance site. The other one, the hurricane completely destroyed the eddy covariance site. So we only have half a year of measurement, so we didn't really use that. And that site we had a year and a half of. We actually had 4.5 years. We had 2 years in 2011, 2012, and then another year and a half in 2021 too. And we used the 11, 12 to parameterize the model and then ran it in forecast mode to see how well we predict 21, 22 without directly parameterize it with that data. So the result that you show was the validation, was the data ran on 21.2 after being calibrated with the previous decade data.
Thank you.
Any other questions for Dr. Bohrer?
No questions, just very interesting. I really appreciate the presentation.
Thank you, Brian.
Brian.
There's some things popping up in the chat.
Yes, thank you, Stuart. Professor, what's next at Old Woman Creek? You talk of what an interesting environment. Are there some things that you want to work on that you haven't had a chance to dive into yet?
Specifically for Old Woman Creek, we're really in full steam on modeling the infiltration, understanding what's getting out of it to kind of work on that annual budget. And we could do the annual nutrient budget as well. I didn't mention it here at all, but it's the same problem. There's a lot of nutrient coming in and coming out and settling. So we know what's settling, we know what's coming in. We need to figure out what's coming out and have a way to model it. That's specific to Old Woman Creek. Big schemes for the further future is kind of generalize that knowledge. So we are working on that in ELM, we are working on links. So there's already an effort from PNNL, not PNNL, Oak Ridge National Lab. There's a researcher there, Ben Sullman, that coupled ELM with a reaction network box. And I'm working with microbiologists in Colorado that sample Old Woman Creek and other wetlands to translate the entire community composition and community metabolic network to a very, very simplistic reaction network. And then use, instead of this hyper simplistic biogeochemistry model that just have methane and carbon, have a little bit more elaborate reaction network model that is inspired by the microbial community composition. So that's the things we're working on now in my group. Big ideas for the future. Compare wetlands around the Great Lakes of the same type that are blocked behind the seasonal sand barrier between areas which are not very more natural. So we have a few in northern Michigan that I know of that are mostly forested versus a mostly agricultural watershed. Compare methane fluxes, compare nutrient cycling in those two wetlands. Does the large agricultural influx of DOC and nutrients really change the functioning of the wetland? Other things we're trying to do is use the data from this wetland and other to calibrate a hydrological model, SWOT, and create kind of a tool for decision maker if you want to create a new wetland. So there's the big H2 Ohio project where there's a lot of money in making wetlands. So if you were to plan a new wetland, you can kind of use our model to run simulations of the nutrient runoff before, well, validate it before you, if you have data of the nutrients, you can then run the model, validate it before you put the wetland, but then simulate the impact of, if I put a wetland here, what will it do? Or if I put a wetland of that depth, of that type, of that area, or if I put it in a different place, where will it get more nutrient reduction, more carbon, more greenhouse, more positive greenhouse budget?
Very interesting. Thank you. Any other questions from the audience? If not, we'll thank Dr. Bohrer again for sharing his time with us today. Very, very interesting presentation indeed. And we'll thank everyone in attendance for spending their lunch hour with us. And we'll remind you that in November, we'll have our next session, which I believe is on the 13th of November. So watch your inbox for an invitation for that, where we'll be hearing from Professor Patrick Basal, one of our new faculty members in the area of geotechnical engineering here in the department. So we look forward to that and to seeing many of you again at that presentation if you have the time on that day. For those of you regarding the CPD for continuing education credits, watch your inbox for those probably within the next week or so. We'll have those out to you. Feel free to contact me with any questions at satterfield.3. That's SATTERFIELD.3@osu.edu if I can be of assistance. And we thank everyone for their time and wish you a wonderful rest of your afternoon. So thanks now and take care.